welcome to Organic Functional Groups Part 2. We're starting with the organic acids, which have what we like to call the Cu group, double bonded O and single bonded OH, which falls at the end of a chain of carbons, or the beginning, I guess, depending on how you look at it. These are most closely related to the esters and can be identified by the fact that they have two oxygens. One is double bonded, and one is single bonded with an H on the end of it. When we want to name an organic acid, if we simply look at our table R example, propanoic acid has 1, 2, 3 carbons. So we're starting with that regular alkane stem of propane. We're going to then drop the E and change the ending to oic acid. Our prefix is from table P. Our suffix is oic acid. We do not need any numbers because the Cu is always on the end. The dissociation of an organic acid, such as ethanoic acid, which we titrated in our acid-base unit, occurs when this little H over here pops up and makes us a free acidic proton. This occurs because of these oxygen molecules here, these oxygen atoms right here, being in such close proximity to that hydrogen. Sorry about that. The high electronegativity of these two oxygens kind of suck electrons away from that hydrogen, thus making it so it's able to dissociate and be that acidic proton. An example of an organic acid is butanoic acid, which smells really bad, so you're lucky you can't smell over YouTube. Fatty acids are a really common thing that you've heard of. You also hear them called triglycerides. As you can see, there's kind of 3 stems to these. What's very interesting is the idea of cis versus trans fats. These are both types of unsaturated fats. In a cis, naturally occurring unsaturated fat, kind of puts a kink in the molecule, which makes it a little easier for your body to basically get rid of. Trans fats, which are produced in labs, are something that we aren't really able to digest as well, break down as well, and they also pack tighter in our bodies. Saturated fats pack pretty tightly as well too, since they have these nice straight chain molecules. And these are some space-filling molecules where you can see this saturated fat right here packed in there really tightly, which is why it's hard for your body to break down. Once you have, these are some double bonds shown here, and you can see that that kind of puts a bend in the molecule, giving some more surface area. Carboxylic acids is another name for the organic acids. This name is used kind of traditionally, so you might hear that from time to time. They occur commonly in nature. They can be liquid at room temperature due to their moderate intermolecular forces, and they have a Cu group that can interact with water because of the high polarity of these molecules. Esters are extremely similar. In an ester molecule, we still have 2 oxygens, and one of them is double bonded. So our ester functional group looks like this. The difference between this and an organic acid is we are going to have carbon chains on either side that can have the same or different numbers of carbons in them. So these are very similar to the orgo acids, and we identify them by looking for 2 O's. One of those will be double bonded, and this is within the carbon chain. Esters can be the most difficult to name. We look at this example of methyl propanoate. This right here is a 1-carbon methyl group that is coming off of the O in the middle of the chain. It's kind of reminiscent of the ethers. On the other side of this, we have 1, 2, 3 carbons, which relate to this propane base in the name. So when we're naming an ester, we're going to first name the substituent off, Again, I apologize. To continue the naming of the esters, we're going to first name the substituent, that single carbon ethyl group. We are going to second name our alkane chain. Since that portion of the molecule of 3 carbons, that would be propane, and we're going to drop that and change that to O8. Our prefix is going to be our substituent. And we also really have another prefix from table P in the second part of that name. Our suffix is going to be O8. And no, we do not need any numbers since we named these two portions of the carbon chain separately, kind of like when we talk about the ethers. We don't need to give a number to position that functional group. They're similar to the organic acids in that we see this bit right here in both molecules. When we actually talk about fatty acids, in reality, they kind of have a lot of similarities to esters, seeing as there's attachments to carbons on both sides of this functional group. Methylethanoate or ethyl acetate is an example of an ester, and it's used as a solvent in paints and things like that. A lot of esters have very strong odors. Actually, many of them very strong, pleasant odors. If you were to go work for a perfume manufacturer, you wanted to make a perfume like Fergie or J.Lo, you would actually be working with ester chemistry. They occur in nature in blueberries and bananas. You can actually create artificial flavors that are these molecules. They have pretty weak intermolecular forces, which allow them to become gases and have strong scents and things like perfumes and food additives. Our last two groups are a little bit different because they have nitrogen in them, the amines and the amides. The amines have a single bonded N in the molecule. You're going to notice in the general formula, this tends to be written like this with these R's indicating different possible atoms that can be on there. In reality, a typical amine actually just is an NH2 off of a carbon chain. Most of the ones we're going to be talking about. These are similar to the amides. Difference between the amines and the amides, both have nitrogen. The amines have no oxygen. Amines are actually used in the formation of amides very often. When we go to name these are very straightforward. If we look at this example of 1-propanamine, we have 1, 2, 3 carbons. That first carbon is where this nitrogen group is attached. So what this really looks like is an NH2 coming off this end here. So we would do our typical alkane stem, propane in this case. We're going to drop the E. We're going to change, it's not drop, it's drop E. We're going to change the ending to amine, and then we're going to add a number to tell where that nitrogen group is attached. So our prefix again will be from table P. Our suffix is amine, and our number, we're going to say, we're going to say yes to this, and it will tell where NH2 is attached to this molecule. Last but not least, we have the amides. Looking pretty similar to the amines, their functional group, excuse me for just a second, actually includes a carbon with a double bonded oxygen. And then this situation over here, which is really pretty much just an amine or amino group. So we're going to have a carbon chain single double bonded to an O. And typically, coming off of this nitrogen, we'll have an H and another group that actually could be a continued carbon chain, or it could just be another H. These are very similar to the amines. These are going to have nitrogen and oxygen. When we want to name the amines, these are very straightforward to name. Propanamine, we started with that propane because we have 3 carbons there. So we're going to start with alkane naming. We're going to follow this up with dropping our E. And then we are going to change the ending to amide. So our prefix will be from table P. Our suffix will be amide. We do not need any numbers. These are typically on the end of the molecule, or they're incorporated in larger molecules, so it's not really considered important. Just a little bit about these. These are actually extremely important biomolecules. Amines are found in a number of molecules in your body and a number of molecules that you actually need, such as the B vitamins. These are a big component of proteins. If you look at an amino acid, it has this NH2 amine group over here, and then it has this Cu group over here. So that's why they're called the amino acids. The R side chain is where the variety in the amino acids come in, which allow them to do different jobs. When you actually string these together and form a peptide bond, by stringing two amino acids together, one from the amine end, one from the acid end, this is when you now create an amide molecule where you have that double bonded O and you have that nitrogen. In DNA, we also see some of these molecules as a little bit of a jump from what we were just talking about, but back to our amino acids, these side chain groups are what give these molecules the ability to all do different jobs. But again, you're starting with a molecule that has an amine, carboxylic acid, you string them together into the amides, and they create enzymes, proteins, all the different things in your body. To wrap this up, talking about some of the functional groups, we have the hydroxy group, which is found in the alcohols, it's an OH. The amino group, which is found in the amines, that NH2. Carbonyl group is a C with a double bonded O. A carboxyl group is the carbonyl group plus that hydroxyl group. You're not really required to know these names, but it is very helpful to kind of be associated with them because people do use them when they speak. Here are some notes that you kind of need to keep in mind. I'm going to fill in some stuff on table R, but you can pause this for a moment and take a look at this. As I go on to table R, there are some things that you need to know about condensed formulas. One of them is when you're identifying an ether, it's important to notice that little O right in there. When you are condensing the formula for an aldehyde, this is CH3CH2. To differentiate this from an alcohol, we actually condense the structural group. It's what I like to affectionately refer to as a CHO. So that's just written that way to differentiate it from alcohols. If we want to write a condensed formula for a ketone, we can now see where this O is in here and the fact that it's double bonded to that carbon. This is different than in the ester, where this O is really in the chain single bonded to each of those carbons. This O is actually, remember, sticking up here as a double bond. Our acids are really easy because we've talked about them. CH3, CH2, COOH is a Cu. We got a Cu group there. The esters, oh, I apologize. That was supposed to go with the acids, my bad. With the esters, we're doing something similar. CH3, CH2, COOCH3, which I affectionately refer to as a cooch. So you do see that double bonded O and that single bonded O condensed down into that condensed formula. So these are formulas that you need to be aware of. They're especially likely to turn up in multiple choice.